Bismillahirrahmanirrahim. Electromagnetic field theory, and this is the second part of the lecture. So, we have discussed the line charges, surface charges, and the volume charges distribution, and we have derived the electric field intensity for these uh, for these mm, so line charges, surface charges, and volume charges. So now the field electric field intensity due to the infinite line charges. Now the charges are distributed along the line, but it limits from minus infinity to plus infinity. Okay, so but and the charges are distributed along the dl small l. So the dz is along the dl is along the z, so we will consider dl as dz. Okay, and these are the position vectors r, capital R, small r, and r1. Okay, so r1 is the position vector from the origin to the source charges, and capital R is the position vector from the source charges and the point charges, and this R is the position vector from the position origin to the point of observation. Okay, the same story as we have discussed in the previous lecture. Okay, now as I have told you that the charges are distributed along the z direction, so the dl, which is the small length of the line charges, is now will be considered a real time value, that is the dz. Okay, r1 is the position vector of the source, and this is, I have discussed this. Okay, so now r1 is along the z-axis while r is along the row. Okay, you can see from the figure. Yes, this r is along the row, so the value for this r1 vector, position vector, is equal to z az r, and position vector, the value for the position vector r is equal to rho a rho. So by head to tail rule we have uh, capital R is equal to r minus r1. Now r1 value is z az, sorry, r value is rho a rho, and r1 value is z az. So this is the value for the r, and for the absolute of r we have rho square plus z square whole square root. So replace this r and r absolute in this formula, so we will get, this is the same formula we have already derived in the line charges. Okay, so rho L, and this was DL in that formula, but now we are taking the real value, that is dz, because the charges are distributed along z direction. So dl dz r minus r1 divided by the 4 pi epsilon naught r minus r1 whole cube. Okay, so de is equal to rho l dz. Okay, now replacing the value of r and r1 over here, similarly the value for the r and minus r1 absolute is this. Okay, so okay, now we have the charges are distributed along the z-axis, and plus z-axis and minus z-axis along the z and minus. So there is a symmetry of electric field intensity along the z and y, along the plus z and the yz. So therefore we have to ignore the minus z portion, and we will consider the plus z. Okay, so for on so neglecting this portion, neglecting this portion, so we will get uh, this portion only. Okay, okay, rho l dz a rho. Okay, ignoring this minus z portion, okay, because the plus z and minus z are equal and opposite, so there is a symmetry between these two. Okay, so taking rho l outside the integration, rho l over 4 pi epsilon naught rho dz a rho, okay, over this. So this is equation number one. Now for the infinite charges, we have to switch we have to switch the z and rho into theta. This is the integration with respect to dz, so which is minus infinity to infinity. If we replace if we take the integration and we have put put it the minus infinity and plus infinity, so the whole result will be infinity. So we will not get the actual value for the e, so that's why we have to switch dz into some theta, so we will get some finite value for the e. So let z is equal to rho cotangent theta. So taking the integration derivative for the z with respect to theta, so we will get dz over d theta uh, is equal to minus rho. The derivative of cotangent theta is cosecant square theta, and the shift this d theta uh, over here. So here is the value of dz and this is the value of z. So we have to replace z and dz in this equation. You have to replace dz over here and z over here, so that the whole equation is now transferred in term of theta. Okay, so now the step is to find the limits because the minus infinity and plus infinity, these minus infinity plus infinity are the limits for the z, but now we have switched the function in term of theta. So now we will have we should have the limits for the theta. So for the limits, z is equal to rho cotangent theta, and cotangent theta is equal to z dividing both side by rho, so we will get z over rho. Now taking the reciprocal, 1 over cotangent theta is equal to this, 1 over cotangent is equal to tangent theta, which is equal to rho over z. Now we have to find the theta. Theta is equal to tangent inverse rho over z. For the upper limit, which is which was the infinity for the case of z, but now for the case of theta we have to replace z is equal to infinity over here. So we will get tangent inverse rho over infinity. Anything divided by infinity is equal to 0, and tangent inverse 0 is equal to 0. So the value for the upper limit of theta is 0. Uh, Now we have to find the lower limit for the z. Z is equal to minus infinity, so replacing minus infinity in this previous equation, so we will get tangent inverse rho over minus theta. So that is the trigonometric rule, that when we will have the negative angle for the tangent inverse, so we can write pi minus tangent inverse of that theta, but positive. Okay, tangent inverse minus theta is equal to pi minus tangent inverse theta. So this is 0, tangent inverse 0 is equal to 0, so we will have pi for the lower limit. Now we have finded the limits, the upper and lower limits for the theta. So transforming the whole uh, function from z dz and these limits into the theta. Okay, so rho as it is rho, now replacing the value of dz from here. Here is the value of this. Okay, so minus rho cosecant square theta d theta, this is the whole actually the dz, and a rho as it is. Now replacing the value for the z, rho square plus rho square plus, and this is the value for the z. Now z is equal to rho cotangent theta. Okay, So rho square cotangent square theta, and this is actually uh, 3 by 2. Okay, so power 3 by 2. Now taking rho square common, so we will get 1 plus cotangent square theta, and cotangent 1 plus cotangent square theta is equal to cosecant square theta. Okay, so the now the rho square cos square theta, cosecant square theta over rho cube cosecant cube theta. Okay, so replacing dividing rho square by rho cube, so we will get rho, and cosecant square by cosecant cube, so we will get 1 over cosecant, which is equal to sine theta. Now the function has been simplified, so now the step we have to do is the integration. The integration of sine theta is minus cos theta. Applying the limits, pi lower limit upper limit is 0, so we will get 2. Now we have 4 in the denominator, dividing 2 by this 4, we will get rho L over 2 pi epsilon naught rho. So this is the equation for the electric field intensity for the line charges, for the infinite line charges. Now the same is the case for the electric field intensity due to the sheet of charges, infinite sheet of charges. Okay, so uh, we have this whole sheet, and now taking the small fraction of that sheet, which is dy and dz. Okay, to dy and dz. So as we know that rho is s is equal to dq over ds. Let ds is equal to dy dz, as I have told you from the figure, that ds is equal to dy dz, two axes. Okay, so from as rho s is equal to dq divided by ds, so replacing ds by dy and dz. Now this is the electric field intensity which we have derived for the line charges. So rho l over, so this relation can be helpful in finding the electric field intensity for the infinite sheet charges. So how this equation can be helpful? We actually have to replace, we have to find AR for the infinite sheet charges. Okay, so uh, have a look on this head to tail rule. This is X. Okay, and this is Y, and this is R. Okay, so this is X, this is Y, and this is R. So by head to tail rule, we have Y plus R, Y plus R is equal to X. This is the resultant. Okay, so R, we have to find the R. We need we are need of R, so R is equal to X minus Y, and this is R. And now the absolute of R is equal to x square plus, which is minus, so minus y whole square, which is x square plus y square whole square root. Okay, so AR is equal to R divided by the R absolute. This is the R value, AR value, and this is actually the R absolute. Okay, so now again moving to the previous section, that is rho L is equal to dq over dl, and dl is equal to dz. So uh, uh, dividing and multiplying both sides by dy, so to get um, so to get the surface charges. Okay, so dy over dy. Okay, now in the denominator we have dy dz, dy dz. Okay, so dy dz, as we have mentioned in previous slide, that dy dz is actually a ds. So replacing this by ds, ds. So and this whole is actually the rho s, surface charge density. Okay, this is actually ds, and dq or ds rho s. Okay, and this is dy, which remains as unchanged. So rho l is equal to rho s into dy. This is the rho l in term of rho s. Now electric field intensity for the line charges, infinite line charges. So actually we have derived the equation for the infinite line charges. So this equation can be helpful in finding the electric field intensity for the infinite sheet of charges. Okay, so now we have to replace rho l by this rho s. Now actually we have done a trick of introducing rho s by this method. Okay, so now we have the rho s dy, and this is the value of ar. Okay, and this is value of r. This is the value of r vector, and this is the value of r absolute. Okay, so and this is the value of r, this r. Okay, so now we have transferred the line, the equation of the line, infinite line charges into the sheet charge, infinite sheet charges. So the final, okay, now again we have two terms, this x and y. So due to symmetry we have to uh, consider only x. Okay, and we will ignore the y portion. So now for the x portion we have this minus infinity to this rho s dy x ax, and we have neglected the y portion axis. Okay, now again we have the again we have the infinite values the for the dy. So we have to transform this y in term of theta, and then we have to find the limits for the y, for the theta, so that we get the finite value for e. Because by this way, if you if you find the integration, you will get the infinite value for the e. So which is not possible and not acceptable as well. Okay, so uh, let y is equal to x cotangent theta, as we have done previously. In that case we have taken z is equal to rho cotangent theta. So now y is equal to x cotangent theta, taking the derivative of y with respect to theta. So we will get dy over d theta is equal to minus x cosecant square theta, and shifting this theta from the denominator along this side, which is d theta. So now we have the value of y and dy, replacing y and dy in the both equation of e in this equation. Okay, so now the limits, before replacing the value of y and dy, we have to find the limits. Okay, in the same method, theta is equal to tangent inverse x by y. And for the lower limit, now in this case they have find the lower limit first. Okay, so replacing y is equal to minus theta, again pi minus tangent inverse this. So we will get theta is equal to pi for the lower limit, and now for the upper limit we will get theta is equal to 0. So the same limits as we have achieved from the line, infinite line charges. So pi to 0. Okay, now replacing the value of y over here. Okay, and dy over here, and now the whole function is transformed in term of theta, and now these are the limits of theta. Okay, so taking x square common from the denominator, so we will get this simple. Okay, now we will get 1 plus cotangent square. So, and then 1 plus cotangent square theta is equal to cosecant square theta. Okay, this is cosecant square theta. This cosecant square by the trigonometric formulas. Okay, so cancel out the x square is will be cancel out with this x square. Okay, now uh, this whole will be equal to 1. Okay, this will be cancelled out with this will cancel out with this, we will get 1, and the integration of 1 is theta. Putting the upper limit and lower limit, we will get this. Okay, so minus will be multiplied with minus 2, we will get plus. So rho s ax over 2 epsilon naught, this is the equation for the electric field intensity due to infinite sheet charges. Now generalizing the above equation, so if this is along the x, now let's suppose we have the n direction. Okay, so we can take the back side of the sheet and replacing the x with minus x, so we will get minus rho s ax over 2 epsilon naught. So this was all about the lecture for the today. Okay, now in this lecture we have studied the electric field intensity due to infinite line charges and infinite sheet of charges. Thank you for the moment.